All right. So welcome back, guys. I think the previous this thing network disturbed us. So please just comment on the chat box. Let me be sure that you guys are following. Just drop you can hear me on the chat box. Thank you. Just the right hand side. Um, hello. Okay, just drop a message on the chat box. Let me be sure you can hear me. Okay. All right. So like I said previously, sorry, network interrupted our class. Like I said previously, we're going to be doing I'll be starting with electrolysis. All right. So we're going to be doing electrolysis. So I'll be sharing my screen shortly. And then while I'm sharing my screen, I'll be using my phone because if I use my phone, I'll be using it to be monitoring whatever we are doing here because once I share my screen, I'll be out of this screen. All right, so let me share my screen briefly. All right, so look at this. I said straight to the point. The first topic we are going to be treating today is electrolysis. Sorry, my ink is faint. All right, my ink is faint. So let's say electrolysis. All right, so we have electrolysis. Now, what is the topic? This topic is under what we call coulometry. I was telling us that the BCH course rep, that's Clever, sent me a PDF material which the lecturer gave him or sent to him. So I'm going to be sharing that material at the end of the class in the group. So please kindly read through the material. It's basically a one-page material, one to 2 pages, right? So it's not much. So just kindly read through it and then get back to just know it. But what we're going to be doing is basically the calculation part of this guy. Now electrolysis has two laws. The first law, Faraday first law, and Faraday second law. But I am not interested in the second law of electrolysis. So what we're interested is in the first law. Okay, now what does this first law state? First law states that the amount of substance, let me just write it out for avoidance of doubt. Amount of substance deposited or liberated during electrolysis is directly proportional to the quantity of electricity passed. Now, this is the first law of electrolysis. I'm sorry, my writing is not bold enough. I don't know why it's like that, but then all right. So now, mathematically, the first law of electrolysis has this formula: M all over capital letter M equals to Q all over NF. Now, the Q is a quantity of electricity which has a formula of I times T. Now, I is a current. The current is in ampere, and the time is in seconds. Now, this formula can be written as this formula is very, very important. The formula is very important. Please, can you see the board? Can you see the board? If you can see the board, just drop a comment. Okay. Now, this M, the small letter M, is a mass deposited or mass liberated. Capital letter M is a molar mass. N is number of moles of electrons. And of course, F is our Faraday's constant. Yeah, the bodies. I don't know why. This stuff is stressing me to use. So let's please just try and manage. I don't know why my ink is not showing clearly. I've tried to fix this stuff a couple of times, but it keeps stressing me out. So I don't really know what to do this time around. All right, so let's look at this question. You just zoom in your screen, right? You can just zoom in your screen. Okay, let me zoom it in for us. Now let me zoom it in. Now you can see that from this formula here, the M is a mass deposited. So anytime you're asked a question in electrolysis, the formula, the one I enclosed in a square bracket, is what you're to look out for. That's the formula, that's the one you're to look out for. The one in a square bracket. Mass, which is small letter m, all over molar mass, which is capital letter M, equals to I times T all over NF. All right, let's just manage. Okay, thank you. Now, so there is a question we are going to solve. Like I said, the question was given to one of the course reps by a lecturer. So I'm just going to Please, I'll expect us to just keep our notes, so that we can jot down this question. All right, I want to read from my WhatsApp. So we have this. Now, this is a question. I feel they might want to ask this question in exams. Okay, the question here is not complete. Let's put down this question. Let's put down this question. The question says, a current, please, if you have your paper, you can write down. A current of, let me see if I can put it down here. A current of 20 milliampere was passed through an aqueous solution. Okay, of iron 3 chloride for 2.5 hours at STP. Now, the first question says, A, calculate the amount of iron deposited at the cathode. B, calculate the volume of Cl2 gas evolved at the anode. Now, they said take molar mass of Fe to be 56. So I read, they said a current of 20 milliampere. Please, if you can write this down, please jot it down. A current of 20 milliampere was passed through an aqueous solution. Where they go? A current of 20 milliampere was passed through an aqueous solution of iron 3 chloride for 2.5 hours at STP. Calculate the amount of iron deposited at the cathode. B, calculate the volume of Cl2 gas evolved at the anode. Please, I want us to get that question straight, right? I just want us to get the question. Now, this is actually the nature of questions you're going to see in your exams under electrolysis. Now, once I'm done with this particular calculation, class, I'm not going to solve questions based on electrolysis again, because any other question you get to see in exams, you should be able to tackle them effectively. Please let me get water. All right, so how do we solve this question? Let's dive into it. First thing first, Class, I'm scrolling up. Let me keep it like this so I can use the upside. I'll say solution. Now, first thing, class, current, which is I, must always be in ampere. They gave us 20 milliampere. So you must convert it to amp. You must convert it to ampere. Class, let me tell us something. Milli, M, has a value of 10 raised to the power of minus 3. Micro has a value of 10 raised to the power of minus 6. Nano has a value of 10 raised to the power of minus 9. So anytime they give you 20 milliampere, remember I said you cannot use milli. You cannot use the current in milliampere to solve. The current must be in ampere. So if I want to remove this milli, I'm simply going to multiply this 20 by the value of milli. So this becomes 20 times 10 raised to the power of minus 3. Okay, so I already did that in my calculator. So I'm just going to say this is basically like saying 0.020 ampere. So that is it. So I've converted the current from milliampere to ampere, right? So I will say for the time must be in seconds. But they gave us 2.5 hours. Give us 2.5 hours. Class, you must convert the time to seconds. Now, how do we convert class? If you're being given hours, from hours to seconds, you're going to multiply by 3,600. So you're going to say 2.5 times 3,600. So when you do that, this gives us 9,000 seconds. Now, there's one thing I would like to explain here. So let me just erase this part. Most of the times, they can give you maybe 2 hours, 30 minutes. Imagine a case whereby the time is given to us in 2 hours, 30 minutes. How do we solve something like this? It's actually very simple. Now, for you to actually get this, it's either you take the minutes to hours or you take the hours to minutes. So I'll simply say 1 hour is 60 minutes, which we all know. 2 hours would be 60 minutes plus this other 30 minutes. So this will give us 90 minutes. Now this will give us 90 minutes. If you now convert this 90 minutes to seconds, this becomes from minutes to seconds is 60. All right, so let's so you can see in a case where we were asked to solve this. So I'll say 9 times 6 is so let's say so guys, so just in case you were asked, just in case you were asked to solve something like this, I made a mistake earlier. 2 hours is 120 minutes. 2 hours is 120 minutes. All right, plus this other 30 minutes. So that is it. Just in case you're being given 1 hour, 20 minutes, convert the hours to minutes, and then multiply by 60 to get your final answer. Okay. Now, the question says, calculate the amount of iron deposited at the cathode. Class, the amount of iron deposited is the mass. The amount of iron deposited is the mass. So I'll say from my formula, first law of electrolysis, M all over capital letter M equals to I times T all over NF. Now what I'm asked to find is the mass. That is what I'm asked to find. All right. So this will simply be, if I make mass subject of a formula, this should be capital letter M. So you cross multiply times I times T all over NF. All right. So how do we get, class, how do we get our N, this small letter N, and how do we get our F? F is a constant. The capital letter M, which is the molar mass, remember, they gave us molar mass of iron to be equal to this. So the molar mass of iron is 56. All right, so let me clear this part again. Class, this iron 3 chloride, this 3 inside the bracket means that the oxidation state of the ion is 3. So our small letter N, please, just in case you're not really seeing the board very well, this particular topic, in those videos I dropped on the group chat, right, I actually treated electrolysis. So on the video of electrolysis, you can check it out. I did something like this, right? So our N is number of electrons or oxidation states of the metal. Now, how do we know the oxidation state of the metal? They said ion 3. So this is going to be Fe3 plus. They said ion 3. So it's going to be Fe3 plus. If they had said ion 2, it would have been Fe2 plus. So this is ion 3. So my N here is equals to 3. So in case you're wondering how we are going to get this N, this is actually how we got it. So from here, let me circle this part. This bracket is ion 3. So how do we get to know the number of electrons or the oxidation state of the metal? By this. Okay. So let's solve for this A. They said calculate the amount of iron deposited at the cathode. And I told us that the amount of iron is capital letter M. So we'll go ahead to clean this part so that we have enough space to solve for that. So this becomes we have capital letter M times I. Now, the molar mass of iron they gave us at the bottom of this question is 56. So you come here, this is 56 times, the current is 0.020, which you can ignore the 0, times the time is 9,000 seconds. Now divided by the number of moles of electron, which is the same thing as the oxidation state of this metal, ion 3, is 3 times the Faraday's constant, which is 96500. Now this becomes equals to 0.0348 grams. So this is the amount of iron that is deposited at the cathode. So please carefully look through this guy. I've minimized the screen. So carefully look through and ask any question. So I'll be checking the phone in case you have a question. Please, do you have any question? The board is so bad. So sorry about that. I've tried to see how I can. Let me see if I can get another board. So, I want to stop sharing my screen. I can get another board. So just give me some couple of minutes. Yeah, someone said, sir, is there a specific kind of calculation for cathode and anode? Yes. Class, for cathode, the deposition takes place at the cathode. That means metals are deposited at the cathode. But for anode, deposition does not take place at the anode, but instead gases are evolved at the anode. Right? The question I asked us, if you look at the example I gave us on the board, or the previous example I asked us to copy down, the first question said we should carry out the calculation at the cathode. Obviously, the second calculation is at the anode. So anode is where reduction takes place. So reduction simply means the metal gains electrons and deposits as a metal solid on the cathode. However, for anode, the non-metals loses electrons and evolves as a gas. So there are different questions. For cathode is always metal depositing, at anode gases, non-metals evolving as a gas. All right. So we're going to be seeing that shortly. Jovi, I'm so sorry. You can't see. The board is messed up. I tried to see if I can get something better, but unfortunately this is our last class for 235 because I'm very sure nobody here will be writing 235 again by God's grace. All right, so I'm trying to see if I can get something better, the board, but I don't know why it's like that. All right, so let's look at the next question. My board, I don't know what's wrong with it. I just wish I'll be able to get something better. All right. Is any other question? Any other question, guys? Can I continue or should I go ahead? We should be interacting now. Eh? All I know you guys are following. These classes. This board is always stressing me out. I don't know why it's always like that. Let's get something better for all of this. Hmm? All right, so Jovi said we should continue. All right, so let's come back here. All right, now looking at the next question. The next question says, calculate the volume. The next question says, calculate the volume of chlorine gas evolved at the anode. Calculate the volume of the chlorine gas evolved at the anode. All right. So we have this. This is what we're going to do, guys. I just want to show something. Now, in this calculation B, we're still going to use mass all over molar mass equals to I times T. Please just pay attention and look at what I'm doing here. Now, this mass over molar mass is same thing as number of moles, which I'm going to use capital letter N. Remember, mass over molar mass is number of moles. All right. So I'm not going to represent this guy with small letter m because we already have a small letter m here, which stands for the number of moles of electrons. All right. This small letter n is different from this capital letter N. Now, this capital letter N is gotten from the normal mole equals to mass all over molar mass. And while this small letter n is actually the number of moles of electrons. Now, before we proceed, let me just give us a preamble of what this guy is. Guys, when we talk about volume of gases, we know that at STP, 1 mole of any gas is always equal to 22.4 liters. This is a known fact. This is actually a known fact that 1 mole of any gas is equals to 22.4. All right. Now, so what we are simply doing here is to look for, maybe I should use red. I think red is better. I think I should use the red color. So let's try this again to see how it's going to reflect on the screen. All right, so we said this number 2, you're asked to solve for the volume of a gas, but they said at STP. The question had earlier said at STP. So we say that, note that 1 mole of any gas is always at STP is always equal to 22.4 liters. This is a known fact, all right? It's actually very constant. It's a known fact. All right, so we're going to say we want to find the mole of chlorine that would be evolved Remember, evolution as a gas takes place at the cathode, at the anode, while deposition as a solid takes place at the cathode. All right. Now, this mass all over molar mass, we are representing it as capital letter N, that is number of moles. All right. This capital letter N is now going to be I times T all over NF. So now, for us to solve the number of moles, the volume, class, what I'm giving you guys now is a shortcut because in exams, there will be no enough time and there will be no enough space. So for this B, this calculation part, this is what you're simply going to do. If you would trust what I'm about to tell you guys now, just follow it in exams. The formula I'm about to give us now is just something you need. So I'll say volume of Cl2 gas at STP is equals to I times T all over NF times 22.4 liters. So take note of this formula. Anytime you're asking, just in exam, just adopt this. You get your answer and you go your way. Now, the only difference, the I we used in the first solving is the same I we are going to use. The time is the same time we are going to use. The only difference is going to be the number of moles of electron. For metals, metal gains electron, they reduces. For non-metal, they lose electron. So the equation of this reaction would be chlorine will lose electron and become 2 moles of chlorine ion will lose electron and become this. So the N for this guy is equals to 2. Please, this question B, listen to what I'm about to say now. This question B is a conventional question. If this question should repeat itself in exams, they will always use chlorine. And if they use chlorine, the N is always equals to 2. That is the equation of the reaction below. So I will now come here and say the only difference between this calculation and the first one is that this N is 2, whereas in the previous calculation, this N was equals to 3, because this metal would receive 3 electrons, right? Excuse me. So we say here, our current, which remember our current here was 0.02 ampere. This was our current. Our time was 9,000. So you come here and you say your current is 0.02 times your time is 9,000. Now the number of moles here is 2 times the Faraday constant is 96500. This is times 22.4. Now, if you do that, this becomes equals to 0.0209 liters. So that is how we solved for that second question. So I will allow us to look through it and then ask questions where necessary. I'll be looking through my phone in case of question. Okay. All right. Any question? Okay. So let's look at, I'll just move down to error and then explain one last question. Remember, the class will be ending by, it's just a 1 hour, 30 minute class. So I will just start up error. So with this now, we have dealt with everything concerning um, electrolysis. So that first part, you can, but let me tell us something. For metals, right, the possible metals that you can see and their various number of moles. Ion 3 is Fe3 plus. Ion 2, the N here is 3. The N here is 2. Magnesium, N here is 2. Aluminium, N here is 3. Lead, N here is 2. Silver, N here is 1. Gold, N here is 1. Which other one? Barium, and so on and so forth. So please take note of all of this just in case of exams. All right, so there is a question I would like to take under errors. Glory, you said I already explained that stuff. I gave us a direct formula, right? There was no need I was trying to solve it the long process, but I thought I said, let me just give you guys a short fault. Now, what we did here is that 22.4, when I get to that point, I'll explain. That 22.4 is basically the volume at STP. So that calculation that you're going to have would be the mole. So whatever you have, you're going to multiply by 22.4. Remember, 1 mole of any gas is 22.4. So if 1 mole of a gas is 22.4, if you have 2 moles, it will be 2 times 22.4. If you have 5 moles, it will be 5 times 22.4. If you have 10 moles, it's going to be 10 times 22.4. So I now said, instead of you going through the process of solving it one after the other, why not just use this formula? I said N, which is our mole, is I times T all over N, F. So whatever you have as your answer, N, you now multiply that with 22.4 to give us the volume. Now this N is a mole. Remember, it's more like saying 1 mole equals to 22.4. So therefore, N mole equals to X. When you cross multiply, X will give you N times 22.4. So that is basically what we did there. Now, someone is saying gravimetric factor. Now, this is what I'm going to do, right? My board is not allowing me, it's not giving me the vibes I want. So once I'm done with error, I must have exhausted the time for the class. So since your exams is in the afternoon, I'll try and make a video for gravimetric factor using a beta board and then post it before 9 a.m. tomorrow, 10 a.m. tomorrow morning, so that you can watch it and then get yourself prepared for exams. Gravimetric factor is just one aspect of gravimetric and CHM235, so you shouldn't really be focusing on that. Those your notes, listen, your lecturer gave you guys notes, those definitions of term, analytical steps, gravimetric analysis, steps involved, digestion, occlusion, all of those, you should actually know them offhand. Make sure you read your notes in between lines. All right. So there's a question I will be bringing up. Someone sent that question to me. So I just want to answer that question. Let's bring it up from my WhatsApp. Now this is a question. This is a question. Please, can we copy that question? Can we copy the question? Can we copy that question out? Let me save it to my system. So once I'm done explaining this guy, oh, okay. No, I'm not going to explain this. I'm not going to explain this. But there's one thing I'm just going to explain. I made a video. One of those links I dropped on the group chat, I explained this particular question. So please just do me a favor to check the group. I'm going to repost the link. All right. So just watch this. I just want to explain one part of this. Then the rest, I already have videos for them. Gravimetric analysis, I'll drop it tomorrow. I thought I was going to do it this night, but my board is very fancy. I don't know all of a sudden why it's doing like that. Let me snap the question so I can write it out. Okay, now look at this. You already have the question, but I just want to write something out. We have site A, 4 points. 4.40. No, that's not site A. Site A we have 2.75, 2.60, 2.65, 2.70. Site B, we have 1.90, 3.00, 2.00, 1.80. Site C, we have 4.40, 4.10, 0.24, 4.30. Yeah, I know some of you guys cannot see clearly. Let me zoom in the screen. I think it's better now. Okay, I think it's better now. So it's better now. So I just, like I said, I already made a video. One of those videos I sent, this particular question is there, but I just want to talk about one thing here. Please, let's jot down that question. All right, now what is actually that stuff I want to explain? Let me categorically state this. I'm not solving the question that was posted or I displayed earlier. That question, I took my time and explained it in the video I posted. The link is on the group chat. But I realized that they did not really ask a particular part that year, but then this is actually a common part that they normally ask, which is, we have three types of errors. We have three types of errors. The three types of errors are the determinate error, the indeterminate error, and the gross error. So now these are the three types of errors. Determinate error, which is same thing as systematic errors. We have determinate error, indeterminate error, and then gross error. So the area I would like to comment here is that they might give you questions like this, and they say you should comment on the type of errors that is present in each site. I repeat, they can give you something like this, and they will ask you to comment on the type of errors that is present in each site. In site A, you can see 2.75, 2.60, and the rest of them. And if you look at that question closely, look through the question again closely, you're going to see that they gave us true value. I'm looking at the question. They said if the true value of total calcium, that means the true value for this first one, the true value for this first one, they gave us to be 2.65. The true value for this second guy, they gave us to be 2.40. And the true value for this guy, they gave us to be 4.05. Remember, error is the difference in magnitude between the measured value and the true value. Now, what is my point? My point is they give us this, and perhaps you're asked to comment on the type of errors that is possible in each site. Comment on the type of errors that is possible in each site. Class, determinate error is characterized, all of them have characteristics. All right, characteristic is something that you look out for. The moment you cite it, you say, okay, this guy is this and this guy is this. Determinate error is characterized by the closeness of the measured values to the true value. I repeat, determinate errors are characterized by the closeness of the measured value to the true value. In other words, accuracy affects determinate error. And what is accuracy? The closeness of a measured value to a true value. Now, the true value for site A is 2.65. This site A, we have 4 replicate measurements. The first measurement gave us 2.75. The second measurement gave us 2.60. The third guy gave us 2.65, and the fourth guy gave us 2.70. So basically, if you look through all these values, right, they are actually close to 2.65. All of them individually are close to 2.65. So therefore, if I'm to comment on the type of errors that is possible in site A, I would say that site A, determinate error is actually found in site A. Why? Because there is a closeness of the measured values to the true value. The measured value are 2.75, 2.60, 2.65, 2.70. These 4 values are closer to 2.65. So therefore, site A is characterized by closeness of the measured value to the true value. In other words, site A is determinate error. Now, how about site B? Now, let me tell us something. This indeterminate error is characterized by random variation, right? Variation simply means the values are not following. Random variation simply means they are not following a particular pattern. As you can see, you have 1.90, you have 3.0, you have 2.0, you have 1.8. The true value is not even close to any one of them. So they are not really close to the true value. All right, unlike the way site A was close to the 2.65. So site B obviously is not determinate error, because determinate errors, the values should be close to the true value. As you can see, these values are scattered. So obviously they are not determinate errors. All right, so how can you or what characterizes this site B is indeterminate error. So the error found in site B can be said to be indeterminate because the values are randomly scattered or the values are randomly spread. Remember, indeterminate error is also known as random error. All right. So when something is actually referred to as random errors, the values are randomly scattered. So you are asked to comment on the type of error that is possible in site B. So you would say error in site B is indeterminate error because they are characterized by random variation. in magnitude and direction. They are characterized by random variation in magnitude and in direction. That is for site B. Now for site C, class, the type of error found in site C is an outlier. Gross error, what characterizes gross error is outlier. What characterizes gross error is outlier. Outlier simply refers to that data value that lies outside the plane, that lies outside the range. We have four values here, 4.4, 4.1, and 4.3. As you can see, these values, and this guy is lying outside the normal range of values. So for the fact that 0.24 is lying outside, it means it is characterized by an outlier. Those that characterizes outlier are the gross errors. Class, let me give us an example of an outlier. Outlier are always either the smallest value or the highest value. That is why they are called outlier. Right? They lie outside the range where other values are meeting. So that's basically what outlier means. So you can see site A is determinate error because it is characterized by closeness of the measured value to the true value. Site B is indeterminate error because it is characterized by random variation of the values. Site C is gross error because it is characterized by an outlier, which is a 0.24. All right, so like I said, I'm going to stop here for today. I was hoping to cover three topics: electrolysis, errors, and gravimetric analysis. So we've done two. Please, the video on error, make sure you watch all of them this night. It's for your own good. Just try as much as you can. If you want to tarry and do it, it's better. So I'll try and see if I can make a video for gravimetric analysis and drop it before morning. All right. So I wish you guys the very best in your exams. So good luck, guys. So if you have any question, please drop it now. I'll actually leave my chat box on for the next 2 minutes. So if you have questions, please drop it. All right. So thank you so much for joining. And please, if you have not subscribed to our channel, please do well to hit the subscribe button. Right? Please subscribe if you have not done so. Subscribe if you have not done so. Please subscribe. All right, please just hit the subscribe button. Thank you very much, and I wish you guys the best. Good night.